This video is about a numerical method called Euler's Method. If you've read the first 3 sections of the text, you'll know that you learned a little bit about modeling with differential equations. You learned about solving certain kinds of separable equations using something called separation of variables to get actual analytic solutions, formulas for solutions. That only works in special cases, so quite often we have to do other things like graph the slope fields to get a feel or a general trend for the solution curves, or use computers with these numerical methods to approximate solutions. And that is the main goal with this method called Euler's Method. Don't say Euler. It's not Euler's Method. It's Euler's Method. Euler's Method kind of hurts my ears a little bit, so please do try to say Euler's Method. It's not the best numerical method for solving differential equations, for approximating their solutions, but it is the most basic and it's the easiest to understand, certainly. And I want to illustrate the geometric idea of Euler's Method by using the CD-ROM that comes with your book. Here it is. And we can illustrate it by going down over here on the lower left to this particular simulation that we can do called Euler's Method. And here we see the setup. In this particular situation, we are limited in the differential equations that we can pick. It's not quite as nice that way as HPG Solver, but this will certainly illustrate the idea of the method. Euler's method applies not to pure differential equations, but rather to initial value problems. You have to have an initial value problem to use Euler's method. Typically, we start our initial value problem at the starting value of 0 for t, though that's not necessarily always the case. And we have some other value, some other starting value for y. Let me just pick, well, I'll just keep it at negative, let's make it negative 0.5. So my initial value problem will consist of this differential equation, which is dy dt equals y plus t. And this initial value, when t equals 0, y equals negative 0.5. That's my initial value problem. I've got different kinds of methods that I can choose over here on the right. It says method and step. I could choose Euler's method with step size 1, meaning delta t equals 1. That's how much t is going to increase by each time. Or delta t equals 0.5 or 0.25. I'm going to go ahead and pick the smallest one of 0.125. Well, I'll pick it slightly bigger, 0.25. To illustrate the method. I'm going to hit this button at the bottom. It says solve. And let's just see what happens when I hit that button. I get a little arrow. Focus on this graph. The arrow is right there, this little blue arrow. Its base point is at the initial condition, t equals 0, y equals negative 0.5. It is a straight arrow, and if you look at the slope field behind it, it does seem to be following the slope field. And that's what solution curves are supposed to do. They're supposed to follow the slope field in such a way that the solution curve is tangent to the slope marks whenever it passes through the center of one. One of the most fundamental ideas in calculus is the use of linear functions to approximate nonlinear functions, or the use of straight lines to approximate curves. The solution of this initial value problem is a curve. But for this tiny interval where delta t is 0.25, that's the horizontal displacement of that arrow, for that tiny interval I'm going to use this straight line segment to approximate the curve. And the idea is that I just keep doing that. Now, it's like I solve a new initial value problem. I go to the tip of that arrow and take that as my new initial condition for my new initial value problem. If you look up on the left here, you'll see some numbers. I started at t equals 0, y equals negative 0.5. Then t went up by 0.25, that's delta t, the change in t. And y went down by negative 0.12. That's the vertical displacement, 0.12 units downward. I will now attempt to place the cursor in the graph at the tip of that arrow. If you look in the top right-hand corner, you'll see that the computer does tell me what my coordinates are for the cursor. I want t equals 0.25 and y equals negative 0.62. I can't quite get it exactly there because it seems, with the cursor at least, to only take even numbers for the hundredth place. But this is close enough to illustrate the idea. Again, it's like that's going to be my new initial condition. I will take the slope field at that point and follow that forward in time by 0.25 units and get a new arrow, which you see under this longer arrow. In fact, it's 1/4 as long because delta t has been picked to be 0.25. These arrows that you see in the field, as I move this around, have a horizontal displacement of 1 no matter where I am. But when delta t is 0.25, like it's what's chosen here, it's 1/4 as long. Notice up in the top left, once again, t went up by 0.25, but y went down less, only by 0.1 instead of 0.12. We continue, we iterate. We do it over and over again for as long as we need to or as long as we can stand, depending on whether we're doing a homework problem or doing it for fun. Go to the tip of that arrow, look in the top right. I want t equals 0.5, y equals 0.72. Let's see. My cursor seems to be stuck. There we go. Oh, lost it. There we go. That's, again, like your new initial condition. Solve it for another half unit of time. Click on that. We get another arrow underneath there. You can see the arrows are starting to curve upwards. And notice in the top left, once again, delta t goes up by 0.25, but y goes down by less this time, by 0.05. Let me just quickly do the rest of this. I won't be as careful. You should be more careful when you do homework problems to get as close to the tip of the arrow as you can. And what we see here are a bunch of straight line segments that are connecting the dots, essentially. That's called a polygonal curve. It's not literally a curve in the usual sense. It's a bunch of straight line segments put together, though the visual illusion is that it looks like a curve. And the hope is that the solution curve is close to that. In fact, it's not the greatest approximation. If I go down here and click Compare All for the given initial condition, the best approximation that this computer program does for this particular initial value problem is given by the top curve that you see. This blue one is the one that we did. And you can see that it underestimates the true solution. It's because these solutions are concave up, and so therefore the tangent lines are always below the curve. That's why we're underestimating it. You can also notice that it gets further and further away as t gets larger and larger. And that's going to be what happens in general. So Euler's method just sort of gives you a little flavor for what numerical differential equation solving is all about. That's the geometric idea. How do we implement it? How do we actually do problems? You need a formula. And Euler's method is based on what's called a recursive or iterative formula. Here's the idea. We're given certain quantities. Pretend that we're given a particular point on a curve. Let me label it t sub k comma y sub k. We're given a step size. Call it delta t. If this reminds you of numerical integration, we are using similar kind of notation here. That's also given, and will take us from t sub k to t sub k plus 1. We're also pretending that we know the differential equation. We know the right-hand side of this first-order differential equation, and therefore we're pretending we know the slope of the slope mark in the slope field through that point. The slope of this is going to be given by plugging the point into the function on the right-hand side. Use this basic idea about linear approximations from calculus. We take this straight line and imagine that that's a good approximation to the curve. Is it really? Well, it depends, but let's just, for the sake of argument, pretend it is a good approximation to the curve. What we'd like to find is this point right up there. We'd like to find the y-coordinate of that point. The t-coordinate is easy. Just add the given delta t to the given t sub k. The y-coordinate, we need to recall a basic fact from your junior high and high school days. Draw a right triangle in there, that the slope of a line segment is rise over run. So, in terms of the symbols that I have here, the slope is given by f of t sub k comma y sub k, the output of the function on the right-hand side at the given point. The rise, well, we don't know the rise, but we can write it in terms of the symbols that we have here. It's the difference, y sub k plus 1 minus y sub k, and the run is delta t. And what I want to do, remember that I want to solve for y sub k plus 1. That's what I'd like to know. So all I need to do is use some algebra to solve this equation down here for y sub k plus 1. Try doing it in your head. Multiply both sides of the equation by delta t. Then add y sub k to both sides of the equation. And here is the equation that gives you the next value of y in terms of the previous value of y and the slope at the previous point and your step size. That's the formula for Euler's method. K is an integer. It starts at 0. We have our given value t sub 0, y sub 0. We start there. And k goes up by 1 each time. It's 1, then 2, then 3, then 4, etc. The other numbers certainly don't have to be integers. And in fact, if you do it by hand, you see that very quickly the decimal calculations you have to do sometimes become kind of painful. But let's do an example. Remember, it applies to initial value problems. In this case, dy dt equals 2t plus y, and y of 0 equals negative 1. I will do like our book does and make a table. Label the first column with k, the second column with t sub k, the third with y sub k, and the fourth with really the change in y, the slope times the change in t. First two columns are easy. K is an integer that starts at 0 and goes up by 1 each time. T sub k, well, I'm starting at 0. Again, I don't have to start at 0, though that's typically what's done. Not always, though. And it goes up by delta t each time. I need to have a value of delta t that will either be given to you in the homework problem, or you will need to decide on it on your own. I'm going to pick 0.5. T is going to go up by 0.5 each time. Like that. So those are the easy columns. The first number in the y column is easy. That's just the starting value of y, -1. Now is where the work comes in. We need to first evaluate this number here. Plug in 0 for t and -1 for y into the right-hand side of the differential equation. I'm going to get 2 times 0 plus -1. Multiply times delta t, which is 0.5. This gives me -0.5, meaning y goes down by 0.5 to -1.5. Iterate. Do it over again. This is my new point now. T is 0.5, y is -1.5. Plug in those numbers into the right-hand side in place of t and y. And multiply times delta t. 2 times 0.5 is 1, plus -1.5 is -0.5, times 0.5 is -0.25. So the new value of y is -1.75. It went down by 0.25. Go one more time. Now take this new point, plug in t equals 1 and y equals -1.75 into the right-hand side. Multiply times 0.5. I think I'm at the limit of doing this in my head. We got 2 times plus -1.75 is positive 0.25. Times a half is going to be positive 0.125. Now y starts to go up. -1.75 plus positive 0.125 is -1.625. Obviously, I could continue this as long as I wanted to get a polygonal curve that I could plot and hope would be close to the true solution. That's the idea of how to do it by hand. Let me just end with a couple things. Let's just check what happens, how this compares with the true solution on the CD-ROM. And then we'll talk about a joke of how, you know, this theme of approximating can be applied to other things, like approximating even 2 times 2. We'll see how to approximate 2 times 2 in a minute. I'm going to go back to the main menu and go to HPG Solver, which if you look at the video for the slope fields I have looked at before. I need to type my differential equation down here. dy dt equals 2t plus y. If you just type 2t plus y in this program, it doesn't quite like it. It's not quite as flexible as Mathematica that way. It says unknown function identifier 2t. Basically, it's telling you it doesn't know that you want to multiply 2 times t. So you have to be explicit and tell it to multiply 2 times t before you add y. And it does know order of operations. It knows to multiply before we add here. If you put parentheses around the t plus y, then it would add before it multiplied. But we want to multiply before we add. We want that one. Take our initial condition. Y was -1 when t is 0. So I'm entering that down here. And I'm going to go down further for y. This should be good enough, I think. And we can draw in the solution. The solution is going to be graphed based on a fancier method called Runge-Kutta. There's the solution curve. How close is it to what we approximated? When t was 1.5, we approximated y to be -1.625. This goes up to 3. 1.5 is about there. So our point, y is -1.625. This is -2 here. It's going to be around here. So the point we'd get t equals 1.5 would be around here. You can see it's below the true curve by perhaps about 1 unit or so. So we're underestimating the true solution. All this talk about numerical methods leads me to thinking about a particular kind of approximation method that engineers and scientists quite often use. I'm titling this, How an Engineer Calculates 2 times 2. Okay? I could replace engineer with scientist or applied mathematician. A pure mathematician wouldn't do this. Hopefully you recall formulas for geometric series. For example, this is a very famous equation. 1 over 1 minus x equals that particular infinite sum. Well, as long as the absolute value of x is less than 1. Engineers and scientists like using equations like this in the following way. They like to use just the linear terms on the right-hand side. Cut off all the nonlinear terms. And use this fact that results, that 1 over 1 minus x is approximately equal to 1 plus x when x is approximately equal to 0. And you can check that that's true. So how would an engineer use that? Well, of course, obviously, an engineer would replace this second 2 with 1 over 1 minus 1/2, right? Obviously. That does equal 2, right? 1 minus 1/2 is a half. 1 over 1/2 is 2. And since engineers like using geometric series so much, why not go up here and replace the x with 1/2, or better yet, cut off the nonlinear terms. Just use this approximation right there. There we go. That's an approximate equation. 1 plus 1/2 is 3/2. So an engineer would approximate 2 times 2 as 3.